Well, thank you very much for inviting me. I'm very happy to be here. I love place-based research because you learn so much that's just not in your own specific field. And you're probably wondering why I'm at NASA. I was trained as a botanist, but NASA looks at paleo studies, so I studied fossil pollen. Things like the last glacial maximum, if we're going to model climate sensitivity and look at how much temperature change occurred, we need to ground truth it. So I'm sort of the ground truther. But I also, our lab is at Lamont, where I get the opportunity to work with geochemists and quite a few other people. And this is sort of a, this talk today combines some sedimentary history with botany and a look at the future a little bit. So right at the beginning, I want to thank everyone who helped take sediment cores. I've been working in Jamaica Bay. I live north of New York City, but I have a kayak and I love to investigate the marshes of the Hudson, and Jamaica Bay is sort of an extension of that. So we've been out there working since the 90s, and as you probably know, Jamaica Bay has been greatly affected by sea level rise. When I started working at Columbia, I decided that we had so many wetlands, and I developed a course that we're still teaching called Wetlands and Climate Change. Because in New York City, you can go to bogs, you can go to salt marshes, you can go to swamps. And if you don't already know, and this group probably does, wetlands are super important for so many reasons. Of course, they're aquifers, they're nurseries for fisheries. I think Jamaica Bay has 325 species of birds, not to mention 90 species of fish. We know from Sandy the protection that wetlands can give. And of course, they're always interesting. This morning's talk on dragonflies and damselflies, that they're at ecotones, you always have interesting animals and plants. For us, they're an amazing archive of environmental history. What's great about the marshes is that the sed rates are high. Sedimentation is higher than lakes. So every 4 centimeters in Piermont Marsh near me is 20 years. So you can get a really high-resolution history. They're also important, we've come to learn, for carbon storage. And actually, I'm excited about local communities along the Hudson coming to us and asking us, how can we value this marsh we have in terms of carbon to put it in our inventory? And that's where we need to go, I think, for the future, because these wetlands have been so undervalued for years. There's a paper that came out in 2014. Some of you may be familiar with it. It was a landmark, well, it's by a landmark person, Costanza, who started to add up ecosystem services. And I don't like that word because it implies they're there for us instead of the wildlife. But the first paper that came out that sort of evaluated the value of wetlands was in 2007. The 2014 analysis measured wetlands 10 times the value that they did in 2007. But we're still losing them at a huge rate. And this new Ramsar report that came out said there's a tremendous loss that's continuing, which is so important for all, for all of those reasons. And one of the things that not many people know, I think, is that New York City is considered a hot spot for sea level rise. And that's for 2 reasons. One is that the rivers coming out bring less water, but also that the North Atlantic overturning is declining, which lessens the sea level pressure and allows sea level to rise. So I just wanted to point that out, that we're facing just because of our locality, an increased potential for sea level rise. And there's a great NASA website, if you haven't seen it and you want to get pictures and understand global warming better. And that's this http climate.nasa.gov. That's where I got these images for you. The top one is actually from an ice core. If we look back in ice core bubbles, we can see the CO2 back 400,000 years. And this is where we are today. That's one of the reasons we know that CO2 is past what we had in the Pleistocene change between ice ages and Holocene warmings or previous interglacial warmings. This trend is the temperature anomaly. I think the average was something like the 30s to 80s. Or, yeah, so this everyone, I think, accepts that temperature rise. And sea level rise globally, the graph on the right is satellite data starting in 1995. And this is in millimeters. This is globally. And of course, that sea level rise is coming from glaciers melting and from the expansion of water just because it's warmer. So I want to get now to our sediment cores and what they tell us. First, I wanted to go over the difference between organic matter and inorganic matter. So organic matter is anything that was living, so plant and animal remains, and inorganic is the mineral matter, the sand, the silt, and the clay. So from the organic matter, we can look at the vegetation and climate history, the carbon and nitrogen history, and we can date single seeds in the core. From the inorganic history, we can look at how the weathering and erosion has changed through time. And we can also see contaminants, although it's interesting that heavy metals like lead and copper actually glom onto organic material just as much or more than mineral material. This morning we had Don's wonderful talk on owls with, so you're familiar with Jamaica Bay if you're not already. And the two cores that I'm going to show you are from Yellow Bar on the western side and Joko Marsh on the right. And there have been several papers showing the losses of the marshes in Jamaica Bay. It's really sad. You could see it. This photo I took along probably around in the 90s of the erosion, partly due to sea level rise, but it's controversial as to what was causing so much of it. So we went out and probed a lot. I was curious about the landward side. The marsh is here, but they look very similar to both of these sites. And as you probably know, there has been longshore transport southeastward, so that Jamaica Bay the Rockaway Inlet used to be only about this extensive, and it has grown as time has gone by. The triangles are the cores that we took, and the circles are the probes. Now, what has been previously known when we started this work was that the tidal range is greatly extended because of the dredging. And the nitrogen load is enormous. And there's a paper showing that when you take a core down 50 centimeters and X-ray it, the density of the plant roots was much less because they already had so much nitrogen, so much fertilizer from the waste treatment plants that come into Jamaica Bay. And we also knew that sea level had been rising, and that can, just because of the inundation history, sort of fragment the marshes. But no one had ever looked to see what else we could learn from sediment cores. So we got a new kind of, between 2000 and 2014, our methods changed. We did have the Livingston piston core, but that kind of compresses marsh sediments, and it's hard to uncompress them to know how the marsh was actually built. So we started using a Russian Dejnowski core, which cuts from the side and takes a meter core. And so these are pictures of the plant remains in those two cores. And we're still working on the remains, but I want to show you what we've done so far. Oh, and let me go back to our questions. So what's the accretion rate? How have these marshes grown in the past compared to their growth today? What can we learn about what we've done to it, humans, and what's natural? And how do they compare? So we came to the western part, and I should mention that elevationally, Joko is a little bit higher than Yellow Bar, although we did find a patch of high marsh grass on Yellow Bar to look at. Now, one of the things, if you download the old topo maps, you see the difference. This used to all be marsh. Look at it now, totally hardened shoreline. So that's the first thing you notice. Now, it used to have 18 streams that brought in sediment. Now we only have 8 and almost no sediment coming in, inorganic sediment. The channels have been deepened 5 meters now versus 1 meter. And it's led to a huge loss of mineral sediment in the marshes and the fragmentation. And I'll show you how we know this. The next thing we do is to look at pollen and spores. And what we do for this is to take the sediment core and take 1 cubic centimeter from each sample that we want. And in this core, we did it, I think, every 4 centimeters. And then we subject it in the lab to all sorts of acids and bases and centrifuging. And at the end of the day, we come up with, it takes 2 days to process 12 samples. But you come up with a pellet of pollen in the bottom of a centrifuge tube. And we put that drop on a slide in oil and count 300 pollen grains per slide. And then from that 300 count, we make a percentage diagram that I'm going to show you. We also screen the larger parts from the core sediment sample to look for things like foraminifera or plant parts, stems and leaves and seeds. That gives us a species-specific answer because, for example, most grass pollen looks alike. It has 1 pore, as like this one. Although Phragmites is much smaller, and we're working on separating the Phragmites. We can also, as I mentioned, date a single seed. This is Salicornia, which is too small. It's only 1 millimeter. And then finally, we burn the samples. That's what loss on ignition is. And if you burn the samples, again, take only 1 cc of sediment, you end up with all the organic material burning off, and what's left is the mineral. And that's what I'm going to show you, the changes through time of the loss of the mineral sediment up to the present. And the last thing I want to show you is we have this X-ray fluorescence spectrometry method. It's called an iTrax machine, and you can put the whole core on this little conveyor belt, and it measures all the metals, all the elements in the core, all the heavy elements. So that gives us a pollution history. And finally, the charcoal we look at. So one of the things about marine cores is it's hard to date something that's not getting its carbon from the air, if you want a good date. And the marshes are great because they're getting their CO2 from the air to make the seeds, and we can then get a date for 1 single seed if it's a big enough seed. The next thing I'm going to show you is the importance of ragweed. That ragweed is native, but when you cut down the trees and open up the canopy for light, that's what comes in, just like poison ivy is native, but it likes light. So we're going to see that in our pollen history. The next thing is we send off the samples to Cornell and get nitrogen content and nitrogen isotopes. And finally, from the XRF, we can get the heavy metals and tie it to the local history. And that's what I'm going to show you. So just to back up a little and go into pollen, because I'm going to show you the pollen diagrams. Palynology was discovered really in the early part of the 20th century. And people realized using the microscope that you could see, it's the male part of the, as you know, pollen in the spring, you can see it everywhere, the male part of the flower from the stigma. And I used to teach in my classes, pollen's the most resistant organic material on Earth. Now we know that leaf waxes are more resistant, so there are people that actually look at leaf waxes as well as pollen. But they're tiny. You can get quantitative results because there's so many of them. And again, you can get a narrow sampling interval. So for example, in this particular situation, when we find more oak and hemlock, we know that it's a little bit cooler, wetter environment than when we find more pine and hickory, because hickory and pine like a drier, warmer environment generally. And then our disturbance species are things like rumex, which is called dock, I think, in the common name, and plantago, which you see cracks in the sidewalk, plantain. And they're from Europe. So let me walk you through this pollen diagram. So this core, which we took in 2000 from Yellow Bar, is over 2 meters. That was a guess, the 1300. These are actual radiocarbon dates that we got on seeds. And if this is depth in the core, each single line there on the y-axis is the percent of that species. So like Picea is spruce, pine is here, hemlock, birch, oak, hickory, elm, sweet gum, beech. And here, this is grass. You can see a big increase in the upper part. Here's ambrosia, which is ragweed, and then these other weedy species. So the first thing you notice is right about here, we see ragweed increasing. This is true in all the lakes for the Northeast, starting in about the mid-1600s. And that tells us that the Europeans came, they cut down trees. You can see the oak decline, the pine decline, hemlock decline. And birch is actually a secondary, so birch doesn't decline that much and comes back. And then ragweed, of course, is increasing. Now again, this is a percent, so if one goes up, the other is pushing down. We also throw in an exotic type of pollen so that we can measure each species and what it's doing individually. But what you see here is that, yes, we did have European disturbance that affected the forests around the marshes. The marshes record it with the ragweed flying into the marsh. The ragweed was not growing in the marsh itself. And then, just like in lakes around New York, we see the 20th century, generally we see a decline in ragweed and a reforestation. And here you don't see the trees coming back as much, but we see grasses. And I'm still trying to figure out if this is, I don't think this is Phragmites much in this core. I think it's actually more, the grasses are blooming more. Basically, there's more pollen, I think. And we'll come back to why that might be. And then the macrofossil diagram, well, I should start with the LOI. This is the LOI, loss on ignition, is when we burned the sample. So what you see is that there's not much organic matter left that burns off. It's very low in organic matter at 2 meters, but it gets more and more organic towards the top of the marsh. Well, what does that mean? Was this a mud flat? That's one of the things we're trying to figure out because we want to know when the marsh is formed. These Jadamina and Trochamina are forams. Miliamina is one as well. These are more high marsh species. Miliamina is more a low marsh. So as the sediment was less organic here, we know it was a lower elevation marsh, and we have the forams that back that up. Then we also find some seeds. This is interesting in the top. There's more Salicornia. Those of you that know salt marshes know this plant. And then Spartina patens and Disticus. So this was actually high marsh, or had high marsh species in it all the way back to here. Now, when we went and got these new cores, this is what we did. Instead of looking at the percent of organic, is we looked at the weight of the organic and the inorganic separately. So if you see an organic increase towards the top, if you just look at that percent, you don't know whether the inorganic was declining or the organic was increasing in weight. So when we look at it and measure just the separate weights, the red here is the inorganic. And you can see that it's dropping off sharply here, back to here, whereas the organic is sort of staying the same. It's not changing as much. Now, if we go over to Joko, which again was a little bit higher, and again, look at how hardened this shoreline is. It's amazing. And those of you who know Jamaica Bay know that Grassy Bay, there's a big pit, right, where they excavated for Kennedy Airport. Okay, so the Joko core is down to 4 meters, and this is the percent again, so it's less than 10% organic. The mud samples, the mud flat samples that I've looked at have less than 0.05% organic matter. So we think that this was just a little bit more than, or starting to be a marsh at this point. Then the pollen record, and this is from the old 2000 core, is similar to Yellow Bar. You can look, again, this is only 2 meters down in the core, but we had a lot more pine and oak before this European impact when we see a decline in oak and pine and this big increase in ragweed and again the weedy species. And I should mention, if anybody knows a good spot in Manhattan, I would love to take a core because I've read all the George Washington's biographies, and during the Battle of the Revolution, they skirmished in Upper Harlem. And he said that when they started skirmishing, it was total woods. They could hide behind the trees. But by the end of the war, of course, the British occupied Manhattan. There was not one tree standing. So that means that ragweed peak would be, amazing in the core. I thought of the Harlem Mere, but they excavated. That was a salt marsh, but they excavated that out, so we can't go core it. But it's one of my hopes, is because you could get the very year, if you could do that. So this pollen record basically shows the same thing that Yellow Bar did. We don't know, this is forams. It's funny, forams are, you can see tiny forams that are the protein inner linings of the forams. They're not the actual shells of the forams, but we see those on the pollen slides. And when we don't see them, I'm not sure what it means in a salt marsh. But this was the new core that we have. We've done the LOI back, this is the LOI only to 1 meter here. You have actually higher marsh more high marsh species and none of the low marsh species in Joko, as you might expect. There's a lot more charcoal in this record, Salicornia again, and then both high marsh plant species here. And again, if you look at the actual inorganic, this time the inorganic's blue, and you see this, again, this sharp decline up towards the present in mineral matter, whereas the organic material in Joko, it seems to be increasing a little bit, but not this huge decline. So why is that? Well, we also looked at, again, the iTrax machine. You can see how fine resolution. It's as fine as you want to pay for it, basically. But you see this big rise in lead, which we can connect to the 1800s, not surprisingly, and copper sort of follows it. And then this is a very busy slide, but I'll start on this side. So this is the new 2014 core with the new kind of core, with the pollen done down to 1.2 meters. Here's where we think the ragweed, the settlement was in 1650. You see that it peaks here in what we think is the 1800s and then declines up to the present. There's a lot of charcoal in this core again. And then I want to walk you through the nitrogen, the zinc, the lead, and the lead isotopes. And over here again, this is just like, this is the inorganic LOI curve, but it's paralleled by titanium. Titanium is an element that comes from the uplands in runoff. So let's go back over here. I've talked about the pollen record. Now nitrogen comes, we know that wetlands naturally clean water. They clean, and it's called denitrification. They put nitrogen back into the atmosphere, N2. But what you see here is that the X's here are the percent nitrogen. You see that percent nitrogen through time just has continued to increase up until this point, which is, and I'll start here, that the nitrogen isotopes are changing here. That's the first wastewater treatment plant that New York City had in 1903. So that's where we see, although there's a percent increase, the nitrogen isotope is changing to heavier values. And then when we get up here, we see tertiary treatment, so actually there is a drop in the total percent of nitrogen. But these are huge amounts of nitrogen in Jamaica Bay. The waste treatment plants, we know zinc is a big factor in wastewater treatment, but we know that laws were passed in 1975, and I should go back to the Clean Air Act in 1962 or 3, I think, and the Clean Water Act in 72. So we think that that's what's helping this decline in charcoal, the clean air, and in lead gasoline, of course, that was 1975. So we are cleaning up, but there's still, of course, a lot of PCBs and other problems in the Hudson. The other thing we could do, James Brown, who's at NASA, looked at the isotopes of lead and matched the isotopes of lead to 1839 emissions in the Midwest from coal burning. So the really neat thing is, I think, from these records that we can try to tie what we see in the cores to local and even regional history. Yellow bar, we didn't tie everything as much, but we can see the same patterns going on in the core. Okay, so what we see when we measure the accretion rate in the marsh, basically the millimeters per year, we see on average that it was about 2.6 for a long time the marshes were accreting. And then, surprisingly, we see this big increase. And that was a big surprise to us because we know that the mineral component was declining. And here's, if you separate these, this is, again, the inorganic or the mineral component through time in this top meter. So we have this huge decline because we've hardened the shore and because we've destroyed all those streams. But what's happened, these open circles, and these are our numbers, show that they have compensated. The organic matter either is more productive because of the high nitrogen, or it's decomposing less. So actually the marshes have been keeping up, but the problem is they're weaker. So that the waves and the action, they're less dense because they don't have that sand, silt, and clay to hold them together. So that was our story. And the problem, I think the solution is, if we, in Jamaica Bay, they started putting thin layer sand and planting Spartina in 2012, I think. And that's working, but the problem is you have huge pits, like Grassy Bay. So until you fill in some of that, if any of you played with mud, you know that the mud goes to the deepest spot, right? In Louisiana, they've actually changed their approach and started filling in some of the channels, the Army Corps, because they've lost over 2,000 acres in the last 10 years or something. But they realize that they have to put sediment in the low places in order for the high places to keep it. Otherwise, it'll wash down into the low places. So finally, in conclusion, we can see this chronology of 350 years. I should point out that those islands were there. We think we've even found a map that has some of the Jamaica Bay Islands on it. But we don't have true mudflat either, although we don't have good dates really far back yet. But we do see the decline in trees, disturbance, and sediment erosion. With the titanium, we see a decline. We see the loss of the mineral matters leading to the weakness of the marshes and the fragmentation that exists. But, and ironically, this huge fertilization we've been doing, we think, must be leading to increased organic marsh content and vertical accretion. So we're keeping up, but we're not being, we don't have strong marshes there. One of the things I also want to point out is if sea level covers these marshes and fragments them all so that these heavy metals go into the estuary, that is not good. There's a lot of heavy metal, especially in the marshes in the southern part of the Hudson and Jamaica Bay. So we want to keep the marshes for all the reasons that they are great. And we just have to figure out how to most effectively do it. Thanks.
Plenty of time for questions.
My name is Daniel Carpenter again. I have a 1904 map of New York City, Long Island, Nassau, and western Suffolk counties. It clearly shows the marshes at that area. And if you'd like to see my map, just call me 631-427-0723.
Good day. Thank you. That was a very complex presentation, and I definitely appreciate it. I'm with Sierra Club. We just did an interview with Professor Burke on the terrapins, on the diamondback terrapins, and actually the day we went, we saw 36 come in and lay eggs. It was quite impressive. He talked about the nitrogen and the everything, fertilization of all the plants, and they actually saying that the terrapins actually were changing their behavior to eat, because they couldn't get through in some places with the green, with the Spartina, with the yep. So that's just an observation, but I think talk about the organic marsh and the content and what's happening, but it's just pretty amazing. Thank you.
I don't know much about it. John probably knows a lot.
Yeah, it's just as a preface, it's refreshing to hear scientists get up and say, we're still trying to figure this out, rather than have all the answers. But my question is, you mentioned a fairly large number of streams that have been destroyed in the Jamaica Bay watershed. My question is, what happened to the stream flow? Where'd it go?
Oh, we know probably the answer. People, right? I mean, you take people diverted, changed streams. Actually, that reference is, I think it's Bob Black. Bob Black, I think, who did so much work in Jamaica Bay. I referenced it in the paper. But yeah, people block streams, they're underground. So even if the water might be flowing in, although only 10% of Jamaica Bay's water is supposed to be from streams or groundwater, the rest of it is waste treatment water.
Well, it's stormwater. That's where you're getting your heavy metals. But again, it's got to be getting there. It's got to still be getting to the bay.
Yeah,
even if it goes through a treatment plant first, it's got to be getting into the bay still.
Right, but it's not bringing clay, silt, and sand anymore. That's the problem. That's the mineral part that helped it hold together.
Okay.
So, thanks, yeah.
You mentioned that you were interested in maybe a suggestion where to take a core in Manhattan.
Yeah,
If you looked at, you're with Columbia, right?
right.
Yeah. So up in the northern tip of Manhattan,
Yeah.
Inwood Hill Park, have you looked around there?
I've tried up there. We keep hitting things.
Yes.
You know, they've made a restoration salt marsh, but we hit.
But I'm just thinking I grew up there, and there were mud flats. At
Were
the
there?
Yes.
Yeah.
There's still a mud flat
Yeah.
at the very tip of the.
So Inwood, up in the...
Yeah, Inwood
yeah.
Hill Park is
Yeah.
up toward the west. And then when you enter the low part of the park and just keep walking north, you see the big C on the
Yeah,
cliff
right.
from that, when they made
Right.
the canal. And right at the very tip is a mud flat. There were clams squirting and whatever when I was a kid there. And I think at least the remnant of that mud flat is still in evidence.
Yeah, we got out there and we
Yeah.
cored. And I have a core from there that has the
I-
highest lead. It's way off the chart. But I couldn't go deeper. I want to go deeper.
okay.
But thank you. We
Yeah.
can try it again, too.
All right.
That's a good suggestion. Yeah.
You mentioned that Long Island is more vulnerable to sea level rise. I wonder maybe if you could explain that a little bit further and maybe offer where we could get some resources on a website or something to read more about it.
Yeah, there are two papers that I could send you. One was this one, they call it a hot spot, at least New York City. So it's partly the way the coast is shaped that storms come up, you know, like Sandy and go barreling up the river, I guess. But the other one was that there's a lessening of North Atlantic overturning, the deep water formation. So if you don't have a high sea level pressure pushing down on the water, sea level can rise more, right? But coastal cities all over the world are vulnerable now because there's another paper that we referenced talking about it's a double whammy because all the rivers have been dammed, right? You can hardly find a coastal city that doesn't have dams. And so there's less flow coming out, too. Well, the Hudson has a Troy Dam, the dam above Troy. And look there are 750 dams on the Hudson. Actually, there are papers on that. They're tiny. A lot of them are tiny. They're old, you know, grist mills, sawmills. That's another thing I want to do is core behind the dams and see what that sediment's like. Because does all the organic float over? Is it mostly mineral? Or is it, what's caught behind there, you know, that we don't have in our marshes downriver? I think it would be great if we took out a lot of the Hudson dams.
There's a old dam on from near the Hudson River at the southern end of West Point Preserve, West Point lands, and there's a stream going up there in a book, and a dam was broken 50 or 80 years ago. So it's gone, the dam is gone, but there's huge sediments many feet thick behind this old dam.
Well, maybe I could get permission, yeah.
And some of the land is actually may not be in the Army area, but West Point area, but maybe the state park. We'd have to get a map and I can show you where it is.
I know where you mean. They used to have a tank sitting over there, the Army did, where that stream comes out.
It's on the west side of Hudson.
Oh, the west side.
Yes.
Oh, okay.
I was up about West Point.
Oh, okay. I thought you meant across from West Point. Okay.
When you mentioned the increase in pollen level from grasses in the sediment, you said something about you guess it's the flowering, increasing flowering. So can you elaborate on that?
Yeah, actually, I don't know. That's a wild guess. But I do see increases in grass pollen, but they're not more marshes, right? There's a declining number. So I don't know. At first I thought in the new core I looked, and there's not much frag. There's a lot of Phragmites, of course, around. But it's not, but that's not the problem. So I'm wondering if, and I haven't looked this up, if the nitrogen could be causing the plant to flower more so that we see more pollen. But that's a wild guess. I don't know.
Thanks.
Or maybe the plants are more dense than they used to be. I guess there's several possibilities. Thanks.